AI governance starts with data. In this topic, we'll connect architecture to the controls that make AI trustworthy: quality, lineage, privacy, consent, provenance, and bias. The goal is to build evidence-ready pipelines that support training, validation, inference, and ISO IEC 1401 alignment. So far, we've built the foundation: ISO IEC 42001 scope, risk governance, accountability, and governed AI architecture. Now we move into the data layer, where trust becomes operational through sourcing, lineage, quality, privacy, bias controls, and lifecycle evidence. In ISO IEC 42001, data architecture is where AI governance becomes practical. Model behavior is shaped long before deployment through sourcing, preparation, labeling, feature engineering, and runtime data. Each step can introduce risks around fairness, privacy, security, explainability, and compliance. That means the architecture must define controls that can be monitored, tested, repeated, and audited. If lineage, access, consent, retention, or quality are unclear, the organization cannot prove control. Strong architecture turns data risk management into evidence, and that evidence is what makes the AI management system credible. Think of AI data as moving through a controlled lifecycle, not as a one-time upload. Data is sourced, ingested, classified, labeled, transformed, and assembled into datasets before it supports training, validation, testing, or inference. At each step, governance should answer 4 questions: who owns the control, what approval is required, what gets logged, and what evidence proves it happened. Separation is essential. Training, validation, test, and runtime data need different access and change controls. Retention and deletion also need to be defined in advance, aligned to legal, contractual, privacy, and business requirements. Governed AI starts before data reaches the platform. Every source needs a registry that records who owns it, how it was collected, what rights apply, and whether consent or licensing limits exist. Ingestion then acts as a controlled checkpoint. Teams validate schemas, authenticate the source, scan for malware, confirm integrity, and remove duplicates before the data is trusted. At the same time, data is classified for sensitivity, business criticality, regulatory relevance, and AI use restrictions. Higher-risk inputs such as third-party data, scraped content, or personal information should require explicit approval before use. Dataset governance begins by defining what the data is, what obligations come with it, and how it may be used. Classification captures sensitivity, personal data, protected attributes, regulatory scope, and business impact. Labeling turns those decisions into usable metadata, including purpose, owner, version, lifecycle stage, retention, consent limits, and risk level. Access is then segmented by environment, so development, experimentation, training, validation, production, and monitoring do not all share the same permissions. Role-based and attribute-based controls ensure people can view, modify, export, label, or approve datasets only when appropriate. Once raw data enters the modeling workflow, every change can affect model behavior. Cleaning, normalization, aggregation, encoding, imputation, deduplication, and feature generation should be documented as controlled transformation logic, not left as ad hoc analyst choices. That logic needs versioning, so teams can reproduce a dataset, compare feature definitions, or roll back if a defect appears. Just as important, training, validation, and test sets must remain separated to prevent leakage and inflated performance. Sampling rules, exclusions, run IDs, feature versions, hashes, and approvals provide evidence that the dataset was created deliberately. Lineage is the chain of evidence behind an AI system. It begins with source context, where the data came from, when it was extracted, who owns it, and whether consent or licensing allows its use. As data is cleaned, labeled, transformed, and versioned, each step should leave metadata behind. That record connects datasets to feature sets, training runs, validation results, deployments, and even inference logs. When something changes or fails, Lineage helps teams trace impact quickly, reproduce model behavior, and answer auditors with evidence instead of memory. Versioning turns model governance from memory into proof. Every dataset used for training or evaluation should have an immutable identifier, supported by evidence such as checksums, timestamps, schema version, and storage location. That version follows the work. Feature definitions, experiment runs, model registry entries, evaluation reports, and approvals all reference the same source. When a dataset or transformation is high risk, especially if it affects protected groups, changes should go through review. The goal is simple. Months later, the team can rebuild the pipeline and explain exactly what produced the model. Readiness starts by proving that data is fit for the specific use case. Before training, measure completeness, accuracy, consistency, timeliness, validity, uniqueness, and relevance. Then set explicit thresholds. How much missing data is allowed, what duplicate rate is acceptable, whether schemas conform, and when outliers become a risk. In production, these checks become continuous monitors for drift, stale sources, pipeline failures, and unusual inputs. A failed check is more than a technical warning. It is a governance event that triggers triage, remediation, approval, or possible model retraining. Bias control starts before modeling, in the data supply chain. Ask who and what the dataset represents across populations, languages, regions, and sensitive groups. Then examine how records were collected, because historical decisions, selection effects, survivorship, measurement gaps, and feedback loops can all distort reality. Labels need the same scrutiny, with clear reviewer guidance, agreement checks, escalation routes, and periodic audits. Outcomes should then be tested with fairness metrics that match the use case, such as disparate impact, equal opportunity, false positive rates, and subgroup performance. The key principle is traceability. Every fairness concern should map to a control and an evidence artifact. In production, the governance question changes. It is no longer only, was the training data appropriate? It becomes, is today's data still behaving as expected? Drift monitoring compares live inputs, labels, populations, missingness, outliers, and freshness against approved baselines. It also watches protected attribute distributions when lawful and appropriate, because changes in who is represented can change risk. Thresholds should be defined before problems occur. When one is crossed, teams investigate, escalate, and decide whether to retrain, roll back, or accept the change. Every alert should feed risk review and continuous improvement. Privacy cannot be added after an AI system is built. It has to shape the data architecture from the beginning. Start by limiting collection and retention to what the approved purpose truly requires. Then reduce identifiability through masking, tokenization, anonymization, pseudonymization, redaction, or synthetic data. Protect what remains with encryption, strong secrets management, access logs, and regular access reviews. Privacy impact assessments should also connect with AI impact assessments, especially when personal data, sensitive attributes, profiling, or automated decisions are involved. The goal is to use data responsibly while minimizing exposure and misuse. Certification readiness means every governance decision leaves a trail. Consent should be tied to the dataset, purpose, processing activity, and any model that uses it. Retention rules should cover each data state: raw, curated, labeled, feature, training, validation, logs, and lineage. Secure use is enforced through policy as code, DLP, export controls, separated environments, and audit logs. The evidence pack proves operation through approvals, access reviews, retention records, deletion certificates, and lineage reports. In an audit, what matters is not intent. It is reproducible proof. The core message is simple. Trustworthy AI starts with governed data architecture. Every dataset needs lifecycle controls, clear lineage, quality checks, bias safeguards, privacy protections, and secure access by design. Together, these controls create evidence for audits, incidents, and certification. Next, we extend this foundation into model lifecycle architecture, generative AI controls, and human oversight with explainability.